Welcome back to Edupedia world. Today we'll see further into refraction on planar surface. Specifically, we will discuss about refraction through a rectangular block. We'll see the ray diagram of refraction happening in a rectangular block. We'll see how exactly it's happening. We'll learn certain terms like lateral shift. And finally, we'll close the chapter with an example. Today's lecture will be focused on refraction through a rectangular glass block. Now, what do I mean when I say a rectangular glass block? It will be something like this, which is a glass which is made out of glass and is rectangular in shape. That is, this surface, let's call it AB, and this surface, let's call it CD, are parallel to each other. Okay. Now this ray of light which is striking the AB surface is the ray of light coming through. Okay. So if I mark this, then this is my angle of incidence. The ray of light is making eye angle with the normal. Let's say this is air, okay, and we know that this is glass. This will again be air. So what is happening is that the ray of light is going from a rarer, that is air, to a denser, that is glass. This is glass, denser medium, and then coming out of it again into the rarer air medium. From our discussion about refraction till now, we know that in traveling from rarer to a denser medium, the light bends towards the normal. Okay, so here what is happening, from rarer to a denser, light is bending. This, if there was no bending of light, then this would have been the original path. But since there is bending, this has deviated towards the normal, and this is the new path. Okay. Now this, if there were nothing more, like if this was completely air and this was completely glass, everything below this, then this ray of light would have continued moving like this, right? And at that time this would have been, this angle would have been the angle of refraction. But here what is happening, we again have an interface between the glass and the air. Now what is happening is the ray of light is traveling from the denser glass to the rarer air, right? And when it's traveling from denser glass to rarer air, it will bend away from the normal, dense to rare, away from the normal. So it will go back this direction rather than the straight path this, it goes back this. And this angle is known as the angle of emergence, represented by E. Okay. Now an interesting phenomena here takes place. What is that? It's the fact that the incident ray, that is this, the incident ray, and this is called the emergent ray. This is called the emergent ray. So the interesting fact which I was talking about is that the incident ray and the emergent ray are parallel to each other. Why so? You can think of it as an extension of the principle of reversibility of light, but I will show the mathematical reasoning behind the two lines being parallel. Let's do this. This AB surface and BC surface are parallel, right? So this angle and this angle will be equal. Since this is normal, so this is the angle of refraction r, this is also angle of refraction r, okay, and this is the angle of incidence I. So by Snell's law, let's say mu, let's assume the refractive index of air is 1, then we can say 1 times sine I is equal to mu, let's represent mu g as refractive index of glass, mu times sine r, this is r. Now when we go at this surface, this takes place at AB, and at CD what happens is that it is bending away. Now this is r and this has mu, so mu times sine r is equal to, again the refractive index of air is 1, right? So this is 1 times sine of angle of emergence, okay, so sine E. Now if we combine this relation, equation 1 and equation 2, we see that this is mu sine r, this is mu sine r. So combining them we get from 1 and 2, we get that sine I is equal to sine of r, which implies angle of incidence is equal to, this will be sine E, angle of emergence. So we get sine of angle of incidence is equal to sine of angle of emergence, which implies angle of incidence is angle of emergence. So in case of a rectangular glass block, refraction takes place in this scenario, this manner, and the angle of incidence is equal to the angle of refraction. Now another interesting fact is, like, this has already proved that this line and this line are parallel to each other, right? Because it's leaving at the same angle as it is going inside. Therefore, what we see is there is a shift in what would have been the path if there were no glass and what is actually the path because of the refraction. So this shift in the path is known as the lateral shift. So lateral shift is the amount of path the ray of light has deviated due to the presence of the glass slab, the rectangular glass slab, right? Now let us see the conditions which determine how much lateral shift will be there. Condition of lateral shift. Sorry about that. Of lateral shift. The first condition, which must have been quite prominent to you, you might have guessed it already, is the thickness of the slab. Like, let's say this is the thickness of the slab. So thickness. How come? What does thickness do? Imagine that the slab was not this thick, but rather from here till here, let's say twice as thick. Then what would have happened is that this line would have further taken this path and traveled like this, in this direction. And after this, here the change of trajectory would have taken place. This lateral line would have come this way, rather the incident line projection would have come this way, and the lateral shift would have been this much. So if we doubled the thickness, then the lateral shift would have doubled. So thickness directly affects the lateral shift. What else? The second factor is at how much angle of incidence the light has struck the first surface. Suppose that the ray of light came straight like this. Okay, let's take a different color. And let's suppose it struck directly. And then here there would have been no refraction. Here there would have been no refraction. The light would have just passed through. And then the lateral shift would have been exactly 0. Now suppose a scenario in which the angle of incidence was further higher than this. Then it would have come somewhere like this, struck here, would have gone something like this, and then further would have moved parallel to this. But since the angle of incidence here would have been large, then the effective shift would have been larger. So more the angle of incidence, more would have been the lateral shift. So second condition is the angle of incidence. The final condition, let's use red again, the final condition on which lateral shift depends is the refractive index of the medium and the wavelength of the light. Those factors, refractive index itself will depend on the wavelength. So if the refractive index is more, then there would have been more deviation here, and as a result the lateral shift would have been larger, right? So we have seen the three factors which affect the lateral shift. Before we jump to the numerical, let's see a real example of the phenomena taking place. Here we see that this is a rectangular block and a ray of light strikes it at this surface. This is equivalent to my AB in the discussion. Now since this is denser, this is I think made out of glass, and this is the medium air. So since this is denser, what is happening is here if we draw the normal, the incidence angle would have been this, and it is bending towards the normal. And over here, since it is going from glass to air, again the light is bending away from the normal. And if we extrapolate this, this is going out straight like this. So this would have been the lateral shift. Okay, now this should help you understand or remember the concept much more clearly. Let's do a numerical now. This question says that a ray of light strikes a glass block of thickness 10 centimeters. So the thickness of the glass block is 10 centimeter and the angle of incidence is 45 degree. We are asked to draw the ray diagram for this whole incidence. Let's draw the ray diagram first. This is the glass block. This has to be perfectly rectangle, and the angle of incidence is 45 degree. So if the light is getting incident on this surface, then it's coming at this angle. Okay, and this is my angle of incidence I, which is 45 degree. Now one thing to note here is that the refractive index of glass will be 1.5. Now we have to apply the Snell's law at this surface. Here refraction is taking place. So first we need to find out what the angle of refraction here will be. For that we will apply Snell's law. Snell's law is mu air, which is 1 times sine of angle of incidence, sine 45, is equal to mu glass, that is 1.5 times sine of refraction, angle of refraction. This implies sine r is equal to sine 45 upon 1.5. So this is sine r is equal to 0.47. This will imply on taking sine inverse 0.47, we'll get r to be equal to sine inverse is equal to 32.6 degrees. So the sine 32.6 degrees is the angle of refraction. So now that we know that the angle of refraction is 32.6 degree, it means that the light will bend towards the normal. Okay, so something like this will happen. This will be, and this angle will be our 32.6 degree. Now again at this surface refraction will again take place, right, and this angle will be 32.6 because this and this are alternate angles. Now as we have already seen in the lecture that the angle of incidence will be equal to angle of emergence, I have shown the proof over there. So we can directly use that concept and say that the angle of emergence here will also be equal to the angle of incidence, which means that the angle of emergence here will be 45 degrees. So this is, let me try it in different color, this is emergence is equal to 45 degree. You can also calculate it, but since we already know, I wrote it. Fine. So using the knowledge of Snell's law and the concept of geometry, we have found out the whole ray diagram. Starting from the incident ray, this is the incident ray, this is the refracted ray, and this is the emergent ray. Fine. Now the final part is telling us to show the lateral shift. Now to show the lateral shift, we need to find the shift in what would have been the ray of light if there was no glass block, and what is the ray of light since there is a glass block. So we need to extrapolate our incident ray. So on extrapolating the incident ray, if you do it right straight, this will turn out to be parallel to this, and this distance will be our lateral shift. And this distance will be same whether we measure it here, whether we measure it here. Anywhere beyond the emergent, beyond this position, the lateral shift will be same. Okay. Now one important thing to note here is that the lateral shift is the perpendicular distance between the extended incident ray and the emergent ray. What I mean by that is that this angle is 90 degree. So you cannot just draw a line like this and say that is the lateral shift. No, the lateral shift is the minimum distance between these two lines, which is equal to the line which is perpendicular. Okay, so with this example, I hope what I discussed in the theory becomes much more elaborate here. In fact, you can actually calculate the value of lateral shift given that we already have the thickness of 10 centimeter here. That will require some knowledge of geometry, and I will leave it up to you to try it as an assignment. It's not very difficult, just a little manipulation and a little geometrical knowledge will help you get that. An important correction in my calculation, I'm sorry about it. I have calculated that sine inverse 0.47 as 32.6 degrees. Rather, it should be 28.03 degree. So the angle of refraction, in this case this angle, should be 28.03 degree. This has been a mistake in the calculation. Kindly rectify it. Thanks.